Okay, Assalamualaikum warahmatullahi wabarakatuh. Here I will explain about the digital transmission systems for final project, the telecommunication system, and I choose transmission system for my explanations, and then introduce myself first. My name is Reza Gustyan Sukmara. I'm from the L44 International class with student ID is 11022201677. Okay, here is the topic of summary. The first one is analog to digital converter, and I will explain how to sampling, how to quantization, and encoding. And the second one is multiplexing, and multiplexing I will explain about the VCM30, VCM24, PDH, and SDH. And the third one is transmission medium, and what is the fiber optic, and how to transmission to the radio, satellite, and others. Okay, here is the introductions. This is the left one is analog signals, and the analog signals has possible infinite values, and then the right one is digital signal, and the digital signal is actually possible values are limited. So why we have to convert to the digital? Because in the real life we just uh, only analog signal, and all of the technology now is a digital signals, and also noise reduction is process. Noise is not accumulated, and digital signal processing, compression, and manipulation of the digital signal, and the coding capability or reduce error and improve quality. And then voices and the data can be combined easy in the processing, and then easy to implementation. I think that's the reason why we have to convert in the analog to the digital signals. Okay, next. Okay, here is analog to digital. For the first one is sampling. Sampling is amplitude modulation process, which is a preparatory step to convert analog signal into digital signals, or uh, PAM signals. And this is the illustration when we doing a sampling. In the left side is input in analog signal, and then sampling here is some kind of switching and become a digital signal like this. And then for the Nyquist sampling theorem, the Nyquist state that to be reconstructible perfectly, then minimum sampling frequency, or FSM, is 2 times the highest frequency of the signal sample. So it means that FMS is equal to 2 times Fmax. This is the formula. And then, for example, we have some cases like this. The frequency of the human voice in range of 300 until 3400 hertz, and we have to determine the minimum sampling frequency for sampling human voice, and then the answer is that Fmax here is equal to 3400 hertz. So FMS is equal to 2 times 3400 here. So it's equal to 6800 samples per second. Okay. And this one is FSM. And if you have, or if we have a questions, or if someone asks you about the, is it okay to sample human voice at speed 8,000 samples per second? And the answer is yes, because the value is more than FSM, I mean. And what happens if the sampling frequency is less from FSM? So the answer is the signal after sampling is cannot perfectly return to the original signal. Yeah, the original signal is analog, right? So it means that there is an aliasing here. There is an aliasing the in our system if we try to less um, FSM. Okay, and this is the aliasing effects. So this is the when the Fs is equal to 2 times F maximum is like this, Nyquist rate here, and this is when Fs is more than 2 times F maximum, and this is an aliasing. So the aliasing is already explained before, and yeah, next. And this is the quantizations or quantizings. The quantizing is the initial process to convert PAM signal to arrangement of digit signals, where the sampling is priced at nearest compressions voltage. So this is the before we quantizations, and after we quantization, maybe there are several different with previous signals here. Okay, and then the quantizing is, for example, this is the formula for the quantizing. For example, we have 3 bits, and we want to convert, and just put the 3 bit into the this formula, and n is equal to 2 in the power of 3, so it's equal to 8. And then the analog quantization size is this one. This is the formula. Q is equal to V maximum and V minimum over big N, and it's equal to this one if we have a 10 voltage for the maximum, and the minimum is 0 voltage, and the result is 1.25 volts. And then this is the quantization mapping samples of continuous amplitude waveform to a finite set of amplitudes. Yeah, this is the example for this is an in and out, and this is the average quantization noise power. This is the formula, and this is the signal peak power. This is a formula also, and signal power to average quantization noise power. This is the formula. Then let's continue to the example. This is the example. This is when we sample the signal. This is the analog signals, and we sample as this one, this one, this one, and the green one. And then after that, this is the level of the quantization, because yeah, and the boundaries is also here because the signal is just until here. So this is the maximum, and also the minimum is like this. This is the boundaries. Signal is until here, and then after that is this one is the quantizing error. Quantizing error is the differences between the input and output of quantizer. So this is the important thing when we want to quantizing some system that we want to convert to the digital. We have to consider about the quantizing error. And then the quantizing, actually there are two kinds of the quantizing or quantizations. There are two types. Here is uniform. So this is the uniform quantization. So as you can see here, A is equal B here. It's like a B, and is and no, the assumption or the explanation is that no assumptions about amplitude statistic and correlation properties of this input, not using the user-related specifications, or abuse too small change in input statistic by not finally tuned to a specific set of input parameters and simple implemented for the uniform quantizer. I'm sorry. And then the application of uniform quantizer is for signal processing and graphic of the video or films and a movie maybe. And then display applications, and process control of applications. And next one is the non-uniform quantizer. So as you can see here, the difference is like this. So the signal is not consistent, and the explanation is using the input statistic to tune quantizer parameter large as an R, then uniform quantizer with the same number of levels, and non-uniform interval is the dynamic range with the same quantization noise actually. And the application of this is commonly used for speech. Okay. And next one is the coding or encoding, and the encoder is used to convert the input bit stream into standard code for transmissions. Some transducer also act as encoders. So this one is when the signal is already quantized before, and then going to the encoder here, and it's become like this. This is already encode. Okay, next ones. So this is the encoder, and the process of encoder. The first one is this one is the signal analog. First, this is the signal analog, and this is a sample first. As I can see previous, this is a sample first, and after the sample, as you can see here, there are decimal values. This is still continuous and or still analog, and then after that we doing sample, so it become like this, and then doing a quantizations, round up and round down the values, and then after that encoding, we just change or convert the number of decimal here become a binary, 01, 10, 10, 11, and others. So that's the process of encoder. And then the encoding for the previous example, because we use the egg um, levels, it means that 3 bits, so become like this. And 0 until 7, or this is a egg levels. So this is the binary that already encoding. And then so the analog to digital converter is the first one is like this. So we have an input signal analog, and after that we sample, and after we sample we quantizer, and after the quantizer, so the encoder, and after the encoder, so we have an output digital signal, as you can see here, the binary form. And then the next one is multiplexing, and the multiplexing is from multiple input to one input, and the function of this is for transmission saving become the basis or base of digital splicing. So I will explain about the PCM30, and the PCM30 is Euro standard, and it has 1 TS of or equal to 8 bit, and consists of 32 TS is 30 sound channels plus 1 sync and plus 1 signaling, and sync is equal to TS zeros, and signaling is equal to TS 16, and videos is equal to TS1 minus 15 plus TS17 minus 31. So in 1 second, TDP 8,000 samples, so that bit rate is equal to 8 times 8,000 times 32. So it's become 2048 kbps for the VCM 30. That's the standard of Europe. And the next one is the VCM 24. This is this American standard, and it has 1 TS is equal to 8 bit as a previous, but consists of 24 TS is equal to 24 sounds channel in the 1 second TDP 8,000, and Synchronization is using one additional bit or PA, and signaling is taken on the eighth bit of each TS on the sixth frame and its multiples. So bitrate is equal to 24 times 8 plus 1 times 8,000. So it's equal to 193 times 8,000 is equal to 1,050 544 kbps for this, and 1 mf is equal to 12 frames. So this one is the multiplexing for the PDS or plesiochronous digital hierarchy, and this is the explanations for the PSD network, almost synchronous, internally pre-running oscillator, and asynchronous multiplexer. If a tributary is converted to a tributary with more bit rate height, is use bit stuffing and additional of the bits is power memory to make it is synchronized with more bit rares such height actually. And yeah, the bit rate it of the attribute or tributary with a higher order more than a simulation of the multiplex bit rate for synchronization signals and bit stuffing. And each multiplex level has its own frame format, and access to the individual channel is possible only after a multiplexing process is carried out. And bitrate standardizations or standardized to 140 Mbps. So it's big, right? It's, yeah. And then this one is HDA as SDH, I mean synchronous digital hierarchy, and the synchronous network internal oscillator synchronized with reference clock and external. So synchronous multiplexer technique, all of the multiplexer signal have identically frame structures, and access to individual channels can be done using pointers without having to demultiplex and everything first, and standardized bit rate based on 155 for Mbps. So this is uh, more than PDH, I think. And move to the transmission medium. This one is the fiber optic, and this is the inside of the fiber optic, and how the fiber optic uh, connected and give what to the objects. So the first one here is input is electrical pulse in, or this is the converted the like electrical like conversations, and an output is like to electrical conversations. So like pulse and like pulse also like this. So this is inside of the fiber optic, and then in this one is inside also of the fiber optic, and in the middle one, the main one here is the glass fiber, and this one is fiber coatings and stretch member, and this is the PCC to protect inside of them, and the fiber will be safe because this is the PVC, and the PVC is good for protect the cable like this. And this is the transmission medium also for the radio. For the first one is multiplexer as we know that before, and then going up to the channel coding, encoder, and modulation up to converter and high power amplifier, and then duplexer, and then after the duplexer go to the antenna, and it will be gone to every radio, And then after that is low noise amplifier, down converter, demodulator, and channel decoder, and demultiplier. I mean demultiplexing. I mean. Okay, here is the last I think for the transmission medium. This is the satellite, and how it works is the first one is the station word to send some data to the satellite here, send the data to the satellite, and then this is the propagation into the nations, and then down to the link here, and this one is the for the receiver is station on the world. And why we have to use the satellite for the transmission? I think it used to be can reach remote areas which has not been reached by the system so far other communication, and can support point to multi-point system or it broadcast I think. So yeah, that's the reason when what why we use the satellite. And the next one is the conclusion. So it's the conclusion, and the conclusion is so to make the digital transmissions, the first we have to do analog to the digital converter to our system that we want to transmissions, and then multiplexings as I previous explained. And then the last one is we can choose according to our case how to spread it, can be by land, by sea, and also by satellite. Okay, maybe that's all for my presentation. I'm sorry if I have mistaken. Thank you very much for your attention. Assalamualaikum warahmatullahi wabarakatuh.